propagator which we have been working with, this x2, x1, has a representation in terms of a set of operators written in the form the ground state expectation value in a harmonic oscillator state of some phi at x2, phi dagger at x1, transpose. Okay, this is where we start. Now, in this entire process, what has happened somewhat afresh when we did this is the possibility of creating and destroying particles. We have not yet connected up the thing completely, which will happen when we do the field theory. But you can start from a ground state, act on it with a creation operator, produce a particle, then destroy the particle again. And we also, when we originally started the entire discussion, we said that this x1 to x2 is only part of the story. The whole physical process which we want to think of is that something produces a particle, and then the particle propagates to another event, and then it gets destroyed. I mean, if you go back to your usual two-slit experiment in quantum mechanics, you have an electron gun which produces the electron. Then there is an interference which happens because of the slits, which is the propagation path, and then in the screen there is a detector. So these three events take place. What we will do now in the next few lectures is to turn this whole thing around. We will latch on to the creation and destruction and show that, remarkably enough, this entire propagator comes out of the creation and destruction event. That is, if you sort of latch on to the head and the tail of this, the rest of it falls in place because of the Lorentz invariance and some of the general principles. This is what we are going to do. Now, compared to the previous one, here we will introduce a few more assumptions, and this is, as I told you, this is an approach essentially pioneered by Schwinger, and I will adapt it for our course purposes. But we will make more assumptions. It might appear as though we are making more assumptions than what is required in the other formalism. But finally, even in this formalism, when you want to connect it up with reality, you have to make equal amount of assumptions. So that is not an issue. And the assumptions are so physically motivated that this gives a very nice way of thinking about the entire process. That is what we are going to do. So the picture which we have in mind is that there is some kind of a source which acts on the space-time, which we will generically denote by some JFX. This simply is motivated by the fact that this classic source in electromagnetism is a current, okay, a 4 current. So you think of a JFX, and X of course is space-time index, so which operates in this space-time and can create and destroy particles. So technically one should have called this as a source plus sink, but we will continue to call it a source. So there is a JFX. The basic operation of the creation and destruction is from some state which we call the vacuum state or a no particle state. So very early on, at t is equal to minus infinity, there is some state which we will call the ground state. And then very late, after the operation of all the sources are ceased, there is another state which we will call 0 plus, which is the ground state relate. It could turn out that these two are the same states. It could also turn out in general that they are different, but we will in general keep them to be different. Now, this is again something which I mentioned very early on. A picture which you should have is that of a time-dependent harmonic oscillator. You start with a harmonic oscillator and switch on a time-dependent perturbation. Before you switch on any of the perturbations, the harmonic oscillator could be at the ground state. You switch on the perturbation and do all kinds of things. At very late times, it can happen, for example, that the asymptotic frequency of the oscillator is different from the frequency you started with. Which means the asymptotic ground state is no longer the same. The future asymptotic ground state is not the same as the past asymptotic ground state, which is what we are translating in the context of the particles. So let us start with these two states. Then the basic amplitude which we want to think of is that you start from a state which is the no particle state very early on, and then you produce one particle with a momentum v. So we see that this process is possible, and which I will write I times some Jp. Okay. This I is put in for future convenience, it will come in handy. So this is the amplitude for a one particle with a momentum p to be produced out of this no particle state, and it is characterized by this function j of p, and this function has to be on shell. So very precisely I should write this as this, but most of the time from the context it will be clear whether it is on shell or not, so I will just denote it as j of p. Okay. This has to be on shell because it is producing a particle with a momentum p and its energy omega. This is some I times j. So this is our fundamental object. Now we want to next look at the amplitude, the corresponding amplitude for a one particle state to go back into the no particle state, and I want to know the amplitude for that. I will show you that this amplitude is actually equal to I Jp star for the weak sources which we will think of. So I want to now first define what a weak source is. Now the moment you switch on the state, all kinds of things can happen. You can have particles can be produced, the particles can interact with each other, etc., etc. And there can be multi-particle production, and you start from an asymptotic no particle state. All kinds of things happen, and then you end up with an asymptotic no particle state again. I'm going to assume that as this thing went on, you are mostly populated by one particle state. That is, the intermediate states are one particle state. There could be many one particle states, in the sense that you can have one particle with a momentum p, one particle with a momentum q, but we are not going to simultaneously have a situation where there are more than one particles in between. Okay. So this is by the assumption that the source is weak and it is only going to produce this one particle state, not the multi-particle state. It turns out that is adequate for our purpose in order to get finally this quantity. So if that is the case, then what one can look at is the following object. We want to relate this to this in the presence of the source, and in order to do that, we will consider the following quantity. Let us look at the same object on P in the absence of the source, that is when there is no source present. Then it is obviously 0 because one particle states are orthogonal to the vacuum state. Now we will expand it in terms of the states in the presence of J. So that will be 0 plus 2, 0 minus. These are the spectrum of states which are present with the J on P. Then this is the no particle state which is put in between. I want to introduce a complete basis of states. Then let us say I am summing over some q, a momentum q, 0 plus 1q, 1q, 1p. Let us make sure we understand what we are doing. You take this object, this is just amplitude in the absence of the source where it is 0, and I rewrite it by introducing a complete set of states in the presence of J. What is the complete set of states? There are no particle state that has to come in. Then there are one particle states which has come in. Then there are two particle state, three particle state, etc., which are all ignored because it is weak. Here is where that weakness assumption comes. Okay. So I have got this, and then I look at this object. Firstly, if you look at this quantity, I am looking at it in the presence of J, and we want to retain to the lowest order. So I can have this as J and this as J is equal to 0, but this at J is equal to 0 is 0. Therefore, that does not contribute. So I can only have this in the presence of J and this in the presence of J is equal to 0. Both in the presence of J is a higher order phenomena which we are going to do. So the lowest order in J is what we are looking. So this is the first thing. Similarly, let us look at this. So this in the presence of J times this in the absence of J is a valid contribution. This in the presence of J and this in the absence of J. Again, this in the absence of J and this in the presence of J. This in the absence of J is 0, so it does not contribute. And both in the presence of J is again a higher order. So this is what we need. What is this? This tells you this quantity in the absence of J is just 1. So this quantity, okay, so this is 1 because in the absence of J nothing happens, so the vacuum state remains the vacuum state. Then you want to look at this, that we had already written. Where have we written this?
Excuse me, sir.
Yeah.
Sir, in the absence of C, 1P is that I can.
Yeah, we will come to that. Okay, it's not 0. Okay, so it's just a question of notation. So let us look at this quantity. This is minus 2p. That minus 2p in the reverse direction is I times jp. So this is the complex conjugate of that. So this is going to be minus I jp star, that is j star of p. Let's make sure you are with me. This is 1. This quantity is the reverse of this. Right? So you have to take a complex conjugate of this, that will become minus and jp star.
So there is there a minus there in that?
Where?
The fourth star.
Here?
Yeah.
No, that is the whole point. This I was put in with a purpose. This is what I am going to prove. Okay, so I haven't proved it yet. Okay, this is the assertion which I am going to give a proof for here. Okay, so this is fine. Then here, this 1p, 1q is just delta p. This is of course 0 if p is not equal to q. But if p is equal to q, there is a term there. And this is the quantity which we are after. And because there is a delta pq, only the q is equal to p term contributes. So what does this relation give? This tells you that take this with a minus sign to the other side. So you get I j of p star equals this quantity, which is plus 1p. So this is exactly the solution. Okay. So that looks like black magic. So let us just understand what is being said and why the die comes in. I'll just give you an intuitive understanding of that. See, what is being done is that if you know how from the no particle state a non particle state is produced, then you can determine for a weak process how from a non particle state you will end up as the no particle state. Okay? Now, if these two states have been the same, then I would have put a minus sign. That is what various people have been asking. But they are not the same. But even when they are not the same, they are related to each other, and this is the relation. Now, why is this peculiarity? Okay, now this is contrary to the spirit of Schwinger, because he would have said that this is the way you should develop things and finally the results will come out. But we roughly know that finally there is going to be some field evolution and things like that, right? So if you look at some evolution operator of the form, say e to the minus ith, and you look at its amplitude between two states, let us say psi and phi, at the lowest order, then what you will get is that in addition to the amplitude in the absence of this is from the one term, then you will get a t I psi h phi. Correct? So what you will find is that the transitions between these two is sort of produced by this H, which is governed by this kind of an amplitude. Now if I interchange phi and psi, this will go to phi and psi, that we are not interested in. Here my phi and psi will go onto the two sides. H is Hermitian. Therefore, the new term is going to be the complex conjugate of this. But nothing will happen to this I. Okay? That is why I pulled out an I. Because that I comes from the e to the minus ith chi. Okay? So that is not relevant for us and everything will work out. Of course, you did not have put that I, then there will be an extra minus sign to worry about. Okay? Fine. So what we have found out is that given this expression, you also have a result that this is equal to this one.
Sir,
Yeah.
can you give one physical example where we can justify our weak source and the time it takes for it?
Oh, we will do all that later on. I mean, when we finally have got the expression, that itself will tell us what a weak source is. And in fact, we will generalize it to strong source by saying that the strong source is built out of several weak sources which are acting in an uncorrelated way. Right now, you just think of a perturbation J, which acts at the lowest order. All the effects will be computed to the lowest order in the perturbation J. J is equal to 0 is your standard background and J acts on it as a it's just like perturbation theory right at the moment. I mean, I need not have said it is a weak source. I could have put an epsilon in front of this J and said that I am working to the lowest order in epsilon. Okay, it's the same thing. Fine. Now we have got up to this. It is also convenient at this stage to introduce a purely space-time representation. This is the momentum space. So the space-time representation, of course, is a Fourier transform. So what we will think of is that this JFP, we will think of as coming from a d4x, which I will convenient just write as dx. This is what I have in mind. JFX, and let us see what sign I should have. I should have e to the IPX here. In our notation, this will come up with a minus IP dot x. So that should go onto the right hand side in our convention. Okay. So these signs will turn out to be important at some stage, but let us keep it there. So similarly, since we also need J star of P will be integral d4x. We will assume the source is real. So J, I am not going to put a J star for this. E to the minus IPX. This is just for simplicity. Okay, so this is the description we have. Just one point. Here our JFX is an arbitrary function of space and time. We are doing the Fourier transform again, keeping P having P0, P1, P2, P3 arbitrary. So this JFP has 4 independent P's sitting inside it. But when we are doing this sort of thing, we are taking it on the Marshall. Okay? So that is only the Marshall things are going to contribute ultimately to the physical processes, but there is no harm in thinking of this as an arbitrary JFP. That is the notation and convention which we are going to use. Okay. Now we want to go further and ask, if I have this kind of a phenomena, is there a physical way I can think of the amplitude for the amplitude for the physical system to make a transition from this state to this state in the presence of J? So this is the ground state to ground state amplitude in the presence of J. We have already seen that path integrals play a crucial role in this, etc., etc. But we want to describe them in terms of this JFP and whatnot. Okay? Fine. So in order to do that, again we will work at the lowest order. So let us write down a general form and then we will determine it. What we mean to say is that, of course, in the absence of J, this is 1. Nothing happens. So in the presence of J, if the J acts on this state and produces a particle, then it is not going to give me a vacuum state. So J has to act at least twice in order to once create and once destroy. So the extra correction term, the leading order correction term is going to be quadratic in J. Then of course there will be higher order terms which we are going to ignore for this. So the quadratic term we will write in this form. It is an arbitrary quadratic functional right now. So we will write it as some j of x, some s of x comma x prime, j at x prime. Okay. See, if j was just a number, the quadratic thing will be j square. But j is a function, so you have to keep one j and another j and integrate over all of them. Because so this is just a general. This is what you would have called a quadratic functional rather than a quadratic function. And there can be some function s here. The only thing which we know about s, and which of course will play a crucial role as we go along, is that it is symmetric. Okay, so but there is one more thing which you can work out at this stage. S can depend only on x minus x prime, even though I wrote it as x comma x prime. Why is that? Well, it is essentially translation invariance, but you have to be a little bit careful. The need you have to be careful is that usually when you talk about translation invariance, you say that, oh, there is nothing in this space-time to distinguish one point from the other, so you can do a translation. You can't do that now because there is a j of x, which is an external source, which depends on space-time. So all points in space are not equal. But you can still get at it by the following way. When you look at an amplitude like this, we expect the vacuum state to be independent of where you put the origin of your coordinate system. So if I make a coordinate system to x plus some L, which is the translation, you don't want this to change. Okay? So if the amplitude which you have written down here should not change, then if I have put an x here and an x prime here and kept an x comma x prime, suppose you change everything by x to x plus a. Alright? So this will go to x plus a, this will go to x plus a, this will become that x bar, this will become x bar, none of them are going to change. Now if it has been s of x comma x bar, it will pick up x plus a and x bar plus a. So the amplitude will pick up a dependence. These things are not going to contribute because of dummy variable, but this s will pick up a dependence, which we don't want. Therefore it can depend only on x minus x prime. I mean, it's essentially translation invariant, but it has to be done with care because there is an external source present. Okay, so you have got this form, and the only condition on s is that s of x is equal to s of minus x. It's a symmetric function. That follows from the fact that you are multiplying by a symmetric function. I mean, s of x comma x bar, only the symmetric part of it contributes. I mean, the anti-symmetric part of it will not contribute because it is integrated with the symmetric function. Okay? We will use this crucially later on, so remember. Fine. So this is the form of this, and we want to get it into that JP, express it in terms of JP and try to determine S. So if you have determined S, we are through. We know the entire thing. Okay. The way we will do that is the following. We will use a physical argument. What we are going to do is to imagine that the source J of x is divided into two parts, with one part acting after the other in some Lorentz triangle. Okay, so you can think of some J of x. I mean, this is just a caricature. In some space time, suppose J of x is not zero here. You draw a line and you think of it as something here and something here. Okay, call this J2 and this is J1. I mean, these are supposed to sort of merge together. So your J is actually J plus J1. Actually J1 plus J1, sorry. Okay, so this J1 acts after J2. Right? This is the kind of configuration we want. I mean, you could have done this in any number of ways, and that is going to final result can depend only on J. But let us think of it as a J2 and J1, with J1 acting after J2, and see what happens. Okay. So here is where the whole argument is very, very physical. So let us ask. You start with a state which is like this, the no particle state, and first your J2 acts on it. Okay. What will J2 do? Okay. Just for convenience of notation, let me call this 1 minus f of some g. Okay, this is a function. This is just a notation to, instead of having to write this entire thing again and again. Okay, so let us go further. Do I want 1 plus or 1 minus is good enough? Okay, so most of the time, let me call it f1 plus, that will avoid some minus. Okay, so what I am going to do is that I switch on my J2 and ask what it does. What it would do is that most of the time it will do nothing because it is a weak source, and occasionally it will do these kind of processes. It will create and destroy or whatever. So you have something like 0 plus 0 minus due to that J2, which I can write as 1 plus f of J2. So here, of course, it is starting from this 0 plus and taking it to 0 minus. It is not doing anything else. Now, similarly, J1 can also do this. But suppose when this J2 acts, every once in a while it will produce a one particle state. The moment it has produced an one particle state, it cannot. It is orthogonal to this. But if my J1 now acts on it, it can kill that one particle state and get it back to the other one. Okay? So when both of them are present, what will happen is that this will get replaced by this quantity times 1 plus f of J1. These two factors tell you what is going to happen if only J2 and only J1 is acting without coordinating among themselves. But plus there is a process in which what you are going to get is that you start with this no particle state, go to a particle with 1p in the presence of J2. This J2 is doing this, it is producing a one particle state. Then that one particle state is killed by J1 with a sum over p. So let us understand this. So let us understand this process. What we are saying is that when both J1 and J2 are present, the contribution to this has two kinds of terms. First kind of term is that they are just acting independently. The J2 first acts, produces a particle and annihilates a particle because it has a quadratic term, it is capable of doing that. Okay, this f of J has a quadratic expression in J. So it just does that. Similarly, J1 also does that. Okay, so that is contributed by this term. Then there is an extra term where this first produces a one particle state like this, which is removed by the J1 acting later on. And the entire expression is for T2, the J2 acting, J1 acting after J2. Okay, that is assumed here. Okay. So this is what you have. So what is this? This can be written fairly easily because first of all we are working at the lowest order. So the product, the only terms which I want to retain are these. It is just 1 plus f of J2 and f of J1. Then you have this extra term. In this extra term, we are talking about from no particle state to a one particle state. That is what we started with. That is denoted by I times Jp. So this is I times J2 of P. Then this is the next one which we have written down here. This to this. That is I times J1 star of P. This is what we have. Okay. However, it is us who divided this J into J1 plus J2. The system does not know any J1 or J2 and it only had a J. Therefore, this should of course be equal to, by our definition, 1 plus f of J. which is 1 plus f of j1 plus j2. Okay? This gives you a nice condition. So let me do that here. What it tells you is that, of course, 1 and 1 goes away. It tells you that f of j1 plus j2, which is here, minus f of j1 minus f of j2. So I am taking those two to the side. Should be equal to, assuming the algebra is all correct, summation over p I j1 star of p I j2 of p. This is a condition on f, and f has this form. This is our f. Okay? The rest is fairly easy. What do? We take this f and substitute for j1 plus j2. You can mentally see what will happen. Okay, so this is a good time to remove the two I factors and write it as minus summation over p of these two quantities. Now if you look at this and you substitute for j1 plus j2 and substitute for j1 plus j2, firstly there is a j1 term that is going to cancel with this. Then there is going to be a j2 term that is going to cancel with this. Then there is a j1 and a j1 term. Both are going to contribute equally because of the symmetry, and that is going to be equal to this. Because both of them are contributing equally by symmetry, I get a factor 2 there, and that minus sign will cancel with this minus sign. So I get a condition that integral dx prime j2 of x s of x minus x prime j1 of x prime is equal to summation over p j1 star of p j2 of p. So I only have to write the right hand side as in space, and then I should be able to read off s of x. So let us see what that is. First of all, the summation over p is our Lorentz-Silvanian integration over d omega t. Then we need j1 p star. We have it somewhere here. Okay, that is j1 p star. Let me write with the x prime. So j1 p star should come from this. That is d4 d of x prime j1 of x prime. Okay, it is actually nicer to write this slightly differently, because I would like to have j1 acting after j2. So let me put this as j1 and this as j2. It's symmetric anyway, so I would like to write it like this. So here I want j1 star of p. j1 star of p is given by this, and that I am going to use x now. So it is dx j1 of x e to the minus ipx. This is coming from this. Then I have another term which is dx prime j2 of p that I need from here. That is j2 of x prime e to the ipx prime. Right? So this is going to be integral over dx prime. Those are taken care of. Then I have a j1 of x. That is fine. then I have an integral over d omega p of e to the minus ip x minus x prime, that is taken care of. Then integral j2 of x. This is what we have. Okay. So now I can immediately read off what is S6 because you compare this with this. So there is a dx prime, j1 of x, j2 of x prime, s of x minus x prime being equal to x. That tells you that s of, instead of x minus x prime, let me write that as a function as x, d omega p of e to the minus ipx, with the condition that x0 is greater than 0. That is, x is after x prime, all the j1s are acting after j2. Remember, that was our whole assumption. So we made that assumption in order to take this process, saying that it first went from a no particle state to a one particle state, then that one particle state went to the vacuum state. The no particle state to one particle state was produced by J2, this was produced by J1. So there is a causal order in which we have implicitly assumed. So this is for x naught greater than 0. This of course is our old friend, we are almost there, but we need to know what it is for x naught less than 0. Okay? That I can do by using the symmetry of S. Okay, when the argument x naught here is positive, I know what the value is. I also know S is symmetric. So I want to know what the S is going to be for negative values of t, which is x naught. Okay. So if t is negative, let me think of the S for a negative value of t, which I will write as minus modulus of t x. Is an explicitly negative value of t, and we are looking at t less than 0. Therefore, modulus of t stands for minus t. Okay, so this is what we want. This, by definition of the symmetry, is equal to S of modulus of t x, where now this is positive, and when this is positive, we know what it is. It is integral over d omega p e to the minus I omega p here times whatever is the time argument, which is modulus of t, plus I p dot x. Okay, this is coming from this, because I now know that t is greater than 0. But of course, modulus of t now I can replace by minus t. So this becomes t, and this becomes sine gets up. Then since omega p depends only on the modulus of p, I can flip the sign of p in order to get it into a Lorentz invariant form. So I get a minus sign here, nothing else changes. So this is equal to the other part of our old friend, d omega p e to the ipx, and this is the value for t less than 0. Very nice. So that tells you that your S of x can be written as theta of t, or rather, yeah, okay, that is fine. Theta of t integral d omega p e to the minus ipx plus theta of minus t integral d omega p e to the I dx. Okay? But what is this? This we have seen millions of times. This is just our x2, x1. So we get a very remarkable result that the 0 plus 0 minus in the presence of J is given by 1 minus half integral say dx prime j at x prime j at x. So this gives a strikingly different and interesting interpretation to the propagator. It's actually going to get better, and in fact you will find that we get more than what we put in, okay, which is the sort of evidence for good physics. What is happening here is that you can imagine this now in terms of a creation, a propagation, followed by an annihilation. Okay? But you will find that it is actually more than that. Okay? That is what we will come to. So we have got this expression, and this is all supposed to be for a weak source. Okay? Now we want to know what is going to happen if the source is strong, in the sense that it can act several times. Now in general, weak source is a well-defined construct. If you want to think of a strong source, then you have to worry about what particles do to each other. In principle, there can be particle interactions among each other. Okay? But there is still a kind of a strong source which you can think of, where many one particles are produced. That is, simultaneously it produces the P, Q, etc. The source sort of divides itself up in some notional sense into parts of it, and each part acts as a weak source. And between the two sources there is no correlation. If that is the case, then you can show that the final result can be written in the, okay, I will probably need some time, we will get to that. Okay? The final result for such a strong source can be written in the following form. I will write it down and then explain. That is a lot easier. It is plus minus in the presence of J is essentially this. You just write it as an exponential. Exponential minus half integral dx prime j at x prime j at x. Now there are several ways of proving this, and I want to prove it using a kind of a physical argument rather than I'll give a mathematical argument as well. So let us first look at this, and let us rewrite this again in terms of our JPs and JP stars. Okay, we obtain this expression here for a J1 and J2. So let us again think of it as a J1 and J2. Okay, if you separate it out, this quantity is what we have been fooling around there, and that is nothing but this quantity. Therefore, in the case when J is equal to J1 plus J2 again, I can write this expression here. Zero minus. First, there is a factor which will come in. This is in the presence of J, just because of J1 or just because of J2. There is a J1 factor. Similarly, there is a J2 factor. Okay. And then the in-between factor which you have is exponential minus half. Okay, the half will go away. So it is summation over P, this thing which we have written down there. J, even the, okay, J1 star of P, J2 of P. It's just this quantity which I am writing it as. Then we know that is what we got it from. Okay? You are with me on this. Now, this is again convenient to write this this as a I and an I, because these are our primary amplitudes. So you write it like this. Now you expand, you use the fact that exponential of a sum is nothing but a product. So you have here plus minus J1. Then you have a product over all momentum states. And for a given momentum state, I have an exponential I, J1 star of P, I, J2 of P. Then I have another plus minus J2. This is just a normalizing factor. Here is where all the interesting things are happening. So there is a product over these quantities. Now you expand your exponentials. Okay? So this will become same thing, product over P. For a given P, there are two exponentials here. These are all C numbers. So first exponential will give you I J1 star of P to the power, let us say some NP upon NP factorial. Okay? Then this one will give you similarly an I square root of NP factorial. I J2 of P to the power NP upon square root of NP factorial. What have I done? Just expanded the exponential. So this is e to the some x. So x to the power n. So I write this as this to the power n, this to the power n, upon NP factorial, which I write as 2 square root, and then of course there is a summation over all NP. So there is a product over P, and for a given P there is a summation over all NP. Okay? Then these are multiplied by this J2 and J1. This in turn can be written in a nicer way. And this last bit I am going to leave it as an exercise for you to work out. Because you need to understand a particular commuting of the summation and the product which occur here. We will write this in a slightly different way. We will define a quantity. This is something which is coming from J2, which is the one which is originally creating things. And this is the one which is going to destroy things. Remember that Ij is from 0 minus the asymptotic vacuum state in the past to a non-particle state. This is from a non-particle state to a vacuum state. So let us think of this quantity and combine it with this and define the following object. 0 to a state defined by a set of integers NP. This is not to a given NP, it is a set of integers NP. This we will define to be with this normalizing factor where nothing happens. G2 times this object here, which is product over P I J2 of P to the power NP upon square root of NP factorial. And similarly another expression, this is from minus, similarly another expression which is you start with a set of particles labeled by NP and you annihilate all of them. So this is again 0 plus 0 minus of J1 product over P I J1 star of P raised to NP upon square root of NP factorial. So once you have defined this, you are supposed to prove that this final expression which we have can be thought of as summation over now not NP but all the sets NP of this quantity. Set NP fine. We are done. Now let us see what this means. What I am claiming is that this entire process which we studied, that is, you started from a ground state at very early times and went to a ground state at very late times, and we have already found the amplitude for that. To the lowest order we rigorously derived it. Then I said if it is a strong source, it is going to go this way, and I am going to give you a proof for this. Now as I said, it can be proved by saying that there are bits and pieces of this J are uncorrelated. I will give you that proof in a minute, but I wanted to give you a physical argument for that. So let us assume that this is true. If this is true, then this result follows. What it is telling you is the following. You start from the vacuum, then you generate a state labeled by a set of integers NP. Okay? So this is that state. Then you destroy that state. Now what is the amplitude for generating that state? That amplitude, except for a normalization factor, is given by the amplitude for generating just one particle in that momentum state, raised to NP divided by root of NP factorial. So this is the amplitude. This is a product, so therefore it is just products of the amplitudes for every P. So if you understand one P, then it is just a product. What is the mode square of this? Mode square of this will give you the mode square of this, which is the probability for creating a one particle state from the vacuum state, right? Rise to the power NP upon NP factorial. So it is like x to the n upon n factorial, and this will give you a e to the minus x. So the entire thing will be a Poisson distribution. So at every mode, you are creating the particles, multi-particles, in the sense that there are NP particles with a momentum p, with a probability which is probability to create one particle rise to the power that integer divided by n factorial. N factorial just tells you that the particles are indistinguishable, and the amplitude for creation of one particle is this, and if all the creation events are independent, you just rise it to the power n. Okay. So the kind of source which we are talking about is a strong source, but it is a source where the creation and annihilations which we are talking about are independent of each other. The particles are non-interacting. So you create some 10 particles, they all propagate, get annihilated, but in between they are not doing anything funny to each other. Okay. So it's a kind of a non-interacting multi-particle state which we are talking about. So this immediately tells you in some physical sense that this is what it should be. Okay. The formal way you will prove this is the following. Let us think of a source J which is expanded into parts, because we know that each of these creation and annihilation events are uncorrelated. So think of it as J1, J2, J3, J4, Jn, large number of them. So you have reduced the strength of J by taking sufficiently large number of them. Each one of them is individually very weak. So if you take any one of those sources, say J alpha, that is going to give you this. This is rigorously true because this is small. Okay, and with the limit of dividing this into infinite number of them with each with the infinitesimal sign, then it is absolutely true. So you have this. So you have this expression, and since it is small, that can be written as exponential minus half integral dx prime j alpha of x to x prime J alpha of x prime. Right? Now, if you take all of them together and you want the total effect of the strong source, then all you need to do is to multiply all the amplitudes together. You multiply the amplitudes over alpha, so you have the net result for J, which is pi over alpha of that quantity. Pi over alpha of this is just a summation in the exponential. So it is exponential minus half summation over alpha integral dx prime j alpha the sandwich, okay, let me write it down, j alpha of x prime j alpha of x prime. Now you see that all the sources are uncorrelated. The definition of uncorrelated source is that if I do dx prime of a j alpha x prime, j beta of x prime, they don't interfere with each other. So this is going to be 0 for alpha not equal to beta. Okay? Therefore, I can write this as a summation over alpha and beta. Okay. Because all the cross terms are going to give me 0. Now you can take the alpha summation into this and beta summation into it and you are done. So that expression is going to be equal to, for the uncorrelated sources, the expression which we obtained earlier. It is exponential minus half integral dx prime summation over j alpha will give you j at x prime j at x. I mean, which is what I originally wrote down. And of course, if you expand it out, it has this nice interpretation of creating several particles at a given momentum state and giving you the result picture. Okay? So, I would like to actually stop here today. What we have shown is that given the external source JFX, there is a nice way in which you can interpret the vacuum to vacuum, the ground state to ground state transition amplitude in terms of this. Now again, if you guys have done the last week's assignment, you would have found that the same thing happens even for a harmonic oscillator. That is, if you take a harmonic oscillator and you put an external perturbation f of t into it, then you can ask what is the amplitude for this oscillator to remain in the ground state if it started out at the ground state. And we can work it out, and you will find it is an exponential minus of a quadratic expression with an integral over just dt with 2 f of t and f of t prime, and in between you will get the Green's function. That is exactly what this is, and if you have Fourier transformed it, you would have got that. But of course, as I said, I want to be true to Sugar's spirit. So essentially we assume nothing, and we did not in particular assume the path integral expression for the propagator. Remember, our original derivation was that Sugar would be the last guy to assume Feynman's path integral. So that suddenly makes sense. So if you, in our original work, we started this as a path integral definition. Then we showed that it has all kinds of properties. Here we have shown this really magical, because what did we assume? We just thought of some nice physical processes, and I said it is a weak source. So therefore Jp is one of them, and then for it to die down, that is from a non-particle state, to go back to the vacuum state should be J star of P. Then we just said that let us look at the simplest weak process which you can have where a particle is produced and destroyed, and wrote down the expression. And we said if I divide this thing into two parts, this is what should happen. Now, you will find actually that there is something very non-trivial in this expression that we will look at in the next lecture. You see, the whole thing has to do with on-shell versus off-shell condition. When we started out, we had a JP and we said that that JP is evaluated on shell. Even when we worked this thing out, we had a summation over P, JP and a JP star, where the P's are on shell. And the summation over P got replaced by an integration over d omega P, which is strictly on shell. We are integrating over d3P, not a d4P integration. Which means that in the end, this expression should not know anything about the off-shell Fourier transform of JFX. You will find that it actually does. Okay? And the reason it does has to do with the fact that the moment you go using the symmetry transformation from t greater than 0 to t less than 0, you are making a very natural but kind of a tacit assumption that everything has to tie together in a particular way in a Lorentz invariant manner. And the moment you do that, the forward propagation and backward propagation get ties together. Here, the xx prime, we know, comes with a theta of t and a theta of minus t. So the interaction between these two works both in the forward direction and in the backward direction. That is what you will find takes it away from the Morse shell. Of course, off the Morse shell, when the omega p and p are not related by the dispersion relation, if you find that there is a probability for the vacuum not to remain a vacuum, then you are sunk, something is going wrong. And you will find that doesn't happen. The mod squares of these will only pick up off-shell things, on-shell things. But outside the, at the amplitude level, it knows about the off-shell propagation. And that leads to very interesting physical effects, which we will discuss in the next lecture, that is tomorrow. Okay, I'll stop there. Questions? Yeah.
So actually, I think I just missed right at the beginning when you wrote down this 0 minus to 1 particle amplitude.
Yes.
Then you said that 1 particle to 0 plus amplitude is
I times the complex
So when
conjugate.
0 minus is 0 plus, it should be just the complex.
No, it is not. Because the 0 plus and 0 minus are not the same states.
No, that's what I'm saying. If suppose my J is just temporal, I mean, it just localized in space time, then my asymptotic vacuum will be the same as.
No, it need not. That is the whole point. Because the moment a source has acted in between, however localized it is, there is a probability that it could have produced a particle. See, you can't say it would not have happened. You see, we will actually see it when we compute this quantity, the mod square of this. But the simplest way to think about this is in terms of just that perturbation expansion which I told you. See, suppose I have an object like e to the minus ixt, okay, which I am approximating as 1 minus iht for a small time interval or whatever. Now if I take psi phi here, I am going to essentially end up getting from this a term which goes like minus it psi h phi. Correct? Now what happens if I interchange phi and psi? Which is what one is doing when one is going from one state to the other, right? If I interchange these two, I pick up a complex conjugate here. But this side doesn't change. Okay? So the origin of these two are different. That is precisely what is happening. So in fact, that is not a serious concern. I need not have put that I there. I could have just worked it out. Only because I put the I, it comes and hits you saying that there is something funny going on, it's not a complex conjugate. But that is exactly what is happening.
Okay, so let me just get this straight. So suppose that the way I was turning on a source was to change one of the parameters of my circuit. Like earlier you were saying that you could have harmonic oscillator time dependent frequency. In that case, I understand that if omega, in the asymptotic path is not the same as omega in the future, then the two vacuum are different.
Right.
But if I'm just putting some classical source, I just turn it on and turn it off, then what does it
No,
mean?
then what you will find is that I j star of p will turn out to be equal to I j p. Okay, there will be a condition on that.
Okay.
Okay, or minus jp. I mean, whatever you are asking for, there is a, if you want a condition between, no, I misunderstood your question. See, what you are saying is that under certain circumstances, it can happen that 0 minus and 0 plus are the same. Yeah, then the kind of sources which will produce this will give you a condition on I j star is equal to minus I j f star. That's all. So j star of p will be j f minus p or minus j f p. So there will be a condition on that j in order for that to be satisfied. But in general, these two states are separate, and that is what we are doing.
And the other thing is, so all this seem to require the source to be weak, but we know that this result is true in general, right?
No, the source, we never said, okay, the original argument for a weak source was done in order to make things very simple and identify this xx prime at the lowest limit. But then we could go from the weak source to the strong source.
And there you were saying that it has to have all this, I mean, all the different j's should be uncorrelated and all these things. But this result is a. I mean,
Yeah, but that is because the j's are uncorrelated. I mean, for an arbitrarily strong source which is producing particles which are, what has gone in is that it's a if you translate it back into field theoretic language, we are talking about a non-interacting field theory in the presence of an external source. What does that mean? That means the particles do not talk to each other. The fact that the particles do not talk to each other in terms of source gives you that uncorrelated condition. Because in general, if you have produced the particles and the particles are interacting with each other, I cannot do any of this. This expression, you said this expression is in general true.
I mean, for a free.
Exactly. It is true only for a free particle theory. I mean, free field theory. So in a free field theory, you are already putting some conditions on the way particles can be produced. You can have any number of particles produced by an external source. But in a free field theory, these particles do not talk to each other. So it is more like a many one particle state rather than a many particle state. That is what is happening.
I have two questions actually. The way we wrote j equal to j1 plus j2, that actually tells us that we have one source and we are just considering two parts of it. Like both of them are acting.
You could have, this has to do with what you mean by one source. If source is for me is just a function j of x. Now a function j of x could have been thought of as the sum of two functions, both having support in some finite domains in the space-time, one completely to the causal cost of the other. I would have still called it one source. But somebody else will say one of them is acting as a source and the other is acting as a sink. Yeah.
So actually we should have put some theta functions in front of the
No, I don't want to do that. That is the whole point. The Schwinger's trick involves thinking of one source as divided into two sets, one acting to the causal cost of the other, and obtaining a result for that, and saying that consistency requires this should be the same as though the only j comes in. That is the final amplitude we wrote down in one way, involve j1 and j2 separately. But we know that it can only depend on j1 plus j2. That is what gave us that condition that f of j1 plus j2 minus f of j1 minus f of j2 should have a particular form. Okay. So this division is a very clever trick in order to obtain that result. Plus the fact that kernel which we wrote down in the middle has to be symmetric. These are the two important assumptions it goes in.
But if we write j1 plus j2, just j1 plus j2, there is no information like which one is acting before the other. So when we wrote the interaction part 0 minus to 0 plus, there could have been a part where j1.
No, but I am assuming that my j is divided in such a way that the all of j1 acts to the future of all of j2. I can always do that. Then I ask what happens. Then I get an expression. Then I say, well, I divided it out. The physics does not know of this division. So physics should only depend on j1 plus j2. Then I get another expression. Then I equate these two expressions. The consistency of that gives you that s of x minus x prime should be this. Okay, that's the way it works. Yeah.
And the second question was, to get that form of f of p, all we assumed was some properties of that S matrix. One was translational in various, the other was s of x is minus of x. And the third was this combining J1 plus J2. And
No, hold on, that is not true. The translational invariance is an assumption, but I wouldn't even call it an assumption, that looks completely natural. The symmetry is definitely not an assumption. You take an arbitrary S of x comma y and plug it into J of x, J of y. Then only S of x comma y plus S of y comma x is going to contribute, just like your tensor index summation. I could have called that my new S. So it is not an assumption at all. It has to be symmetric because it is hit with a J of x prime. Okay? So that assumption is not there. What is the third one?
this combined effect of two can be thought of as one acting before the other.
Yeah, but that is also not an assumption. Because I can always take a source and divide it by a line.
So then if we get finally the propagator
Yeah.
of the relativistic particle, where is the information about the action actually came in? Where
That is exactly what Julian Sugar tells you. You don't need any information about the action. You don't need any information about the field. And you don't even need fields. You can do everything with sources, and that is why it is called source theory. That is really true.
But if
Then he will derive the fields and action out of it. I am only going to use his first chapter, so we will not go into that. But that is definitely right. There are some subtleties involved which I should mention. For example, all that we know is that two integral expressions. One integral involving dx prime of j of x prime, s of x minus x prime should be equal to another integral expression which involves the same kind of a thing with on the right hand side the propagator appearing. These two integrals should match. Of course, they have to match for every j of x. Okay? Then we are going to say the integrands are the same. That has some subtleties, but it can be justified very rigorously by a postulate called the space-time uniformity, which he discusses in his book. So there are some assumptions like that which has gone in. Lorentz invariance has gone in crucially from start to finish. Okay, that is another input which has gone in. But what it tells you is that the relativistic field theory, where you bring in these two principles together, is very strongly constrained system. I mean, a lot of information can be obtained from using these elementary physical processes.
and on one hand the propagator is for a free relativistic particle, so there are no interactions.
Yes.
And we are saying that that is same as
Exactly.
So
Exactly. That was the same point he was also raising. If the particles start interacting with each other, this kind of uncorrelated nature of this thing will not capture the full amplitude, because the particles will do things to each other.
But without interaction, then what are these? How can we think about this?
No, you are saying that the particles are interacting with an external source. They are not interacting with each other.
Huh.
Yeah. So that can always happen, right? The J of x interacts with the particles, so it can produce particles and destroy particles. But once it has produced 33 different particles, the particles are not going to interact with each other.
But in the relativistic particle case, we did not have any interaction or any source.
Oh, but that is because in the relativistic interaction, the relativistic theory, we only talked about this. We never said how the particle was created or destroyed. So we are going one step further. We are now saying that there is an amplitude for it to be created, then an amplitude for it to be destroyed later.
I mean, it's like turning on a current that photons don't talk to each other. But
Absolutely. That's correct. That is one way of thinking about it. Yeah. Photons talk to each other only at a higher order process, right? So the lowest order, they don't talk to each other.
So,
Yeah.
actually, when we expand that exponential,
Right.
we cancel half. How is it?
What half did we cancel?
When we took the strong case,
Yeah.
Yeah, before that rigorous proof we done, what physical.
No, you are saying there is some half which is missing here or something? No, I think this is correct. Yeah.
No, not this proof. Before.
Yeah.
Before the proof we.
Oh, okay. That comes. Okay, I'll tell you. I think I know what you are talking about. When you have f of j1 plus j2,
Yes.
it gives you, when you substitute into this, let us look at one of these experiments. Yeah, here if I put j1 plus j2 and I put j1 plus j2 here, I first get a term with a j1 and j1.
Yes.
That will give me my f of j1 with the half factor and all.
Yes.
Then I get a j2 and j2. That will give me f of j2. Now I will get a j1 j2 and a j2 j1. But because of symmetry, these two contribute the same.
But now the question is, J2 cannot act before J1.
That is fine, but the moment you have got up to this point, when you are writing J1 and J2, it is just a numerical integral. So purely mathematically, if I interchange those two in the integral with a dummy variable,
Yes.
the contributions are the same.
Yes, but they are like operators, means not.
No, they are not like operated. They are all C numbers and these are just functions which are being integrated. Okay? Therefore, that half goes away. Otherwise, you can retain both of them. Then you will get a symmetrized expression which will be equal to this. You will again get the same result.
And sir, one more thing is, we are saying vacuum plus and minus
Right.
kind of thing. Is that something to do with normal ordering with defect?
No, no. We haven't even gone to that, and as I said, Schwinger will turn in his grave. I mean, there are no normal ordering. This is one theory in which there are no infinities. Okay, no divergences of any kind. I mean, so certainly no normal ordering is.
Then why we are distinguishing them? Means if we are creating also and destroying also particles.
Yeah.
If
Okay.
everything is
So
same,
the-
source is also there as it is. Then
Right. That has to do with the fact that your particles at asymptotic minus infinity may not be the particles at asymptotic future infinity. The simplest way to think about this is to think of a harmonic oscillator with a time dependent frequency, which goes from a frequency omega 1 to a frequency omega 2 slowly. Suppose it goes very, very gently. And suppose I put the original system at the first excited state. Then it will go to the first excited state at the late time. But the energy of that system, or even in the ground state, the energy of that system is h cross omega 1 in one case, h cross omega 2 in the other. Now, in the new harmonic oscillator context at late times, the kind of particles you are thinking of and their energy spectrum are different from the particles which you are thinking of in the asymptotic past. So, what you call particles is already changed in such that kind of an interpretation. But this is precisely what Gaurav was also asking. It may happen that in some context, 0 plus is the same as 0 minus. There is no real particle production. It doesn't matter. Our formalism will take care of it. We are looking at a more general context. So if it turns out to be the same, then there will be some conditions on what kind of source you are putting.
Okay, you just said that there are no infinities here. So,
Yeah.
what about the amplitude go from x to x? I mean, that turned out to be infinite earlier when we calculated it, right?
Yeah, when I said there are no infinities, in physical processes there are no infinities. That is, if you compute this quantity with x and x prime, you are not going to get contribution from x is equal to x prime itself, because that is the set of zero measure. When you do this integral, you will get a finite answer. Okay, so that is again the spirit in which Schwinger will be developing this. He will say that, okay, let us think in terms of what in a lab you will be looking at. There is a beam of particles, and then the particles are doing something, and in the end that beam disappears. And I will tell you how to compute things for that, or how to compute S matrix elements, etc. And anything which is not observable, I don't care about.
So,
Yeah.
there was this calculation initially, the one that you referred to as black magic, right? Like where you actually got 5 GB star.
Yes.
So, like initially you had one particle going to 0 plus,
Right.
which you put as equal to 0.
Yes. In the absence of the source.
Yeah.
That is, it is just a trick. I mean, you take the orthogonality of one particle state and the no particle state in the absence of the source, because in the absence of the source they are orthogonal, and you expand the same quantity in terms of the states in the presence of the source,
Yes.
which is a complete basis.
That is true.
Yeah.
And then what you do is, so on the left hand side you have g equal to 0.
In the left hand side you just have 0. I mean,
You have
because
0. But,
yeah.
Then when you expand it, you have these terms. And
Yes.
You have terms like, you have terms with g equal to 0 and then you take.
No. When you expand it, you typically get products of two amplitudes. Sometimes these kinds of questions you should stop then and there and ask me, because I don't have the expression with me. I mean, it is wiped out. So what is going to happen is that in the two amplitudes, we are going to say that we are looking at the weak J limit. So to the lowest order. So in the lowest order, when you look at two terms, there will be only one term which will contribute in each of the amplitudes. The other term will go to 0. So as a result of it, you get a condition.
But I'm still confused because you have this thing, you expand it.
Right.
So you have like 0, 1p.
Right.
and then expand.
Why don't we do that again? See, what I did was, let us look at, I think I looked at this. You can get it from different terms. I think this is what I looked at, right? You have the notes with you.
0 plus, right?
Sorry?
0 plus.
Did I look at 0 plus? Yeah, okay, 0 plus. Okay, fine. So you take this and this is 0 when j is 0. Okay? Now I am going to expand this out. So I have this. Then I want to introduce a complete set of bases in the middle. So I am going to have 0 minus and a 0 minus 1p in the no particle state. Then I am going to add a 1 particle state. Q, 1 particle state Q, 1p. Okay, this is what I did. So I had just taken this and expanded in this basis. Now what I argued was that if you look at this object, if I switch on J, the effect with J on both of this is a second order. I want to stick to linear order in J. To the linear order in J, if I take presence of J here and absence of J here, okay, or I can have absence of J here and presence of J here. Now, in the absence of J, this is 0. Therefore, this term will not contribute unless I keep a J here. Then I have to keep J is equal to 0 here. Okay? Similarly, this is not going to contribute in the absence of J, so I have to have a J here. Therefore, I have to put J is equal to 0 here. This quantity is 1. This quantity is what we have defined as something. Then this quantity is delta PQ. The rest follows.
My doubt is like first we have assumed j equal to 0 to get it to be equal to 0.
No, that we have not assumed J is equal to 0. I am saying consider this amplitude in the absence of J is equal to 0, that is 0. These states I am going to expand in any other complete basis states, and I choose for my complete basis the states in the presence of J.
But that then you use the condition that a have to be 0 when j equal to 0.
What have to be 0 when J is equal to 0?
Okay, I'm still confused.
Yeah, where did you just think about that? Yeah. Any other questions? Okay, we'll meet tomorrow.